Good afternoon. So in the next 90 minutes, I would like to talk with you a little bit about a project with my friend, colleague, co-author, Kobe Jacob Glaser. Those of you who don't know him, here is a guy. That's a picture that I took of him in our lab. Our lab, of course, is a cafe in Tel Aviv. Actually, that's exactly the table where actually the main idea of the paper that I will talk about was created. That's the historical moment, more or less. So the project is a little bit about, about the general topic that is called mechanism design and bounded rationality. Some of actually the papers that we created in the last 15 or 18, 20 years on the subject actually are included in a short book that appears in a series that Eric is editing. I brought with me about 20 copies of the book. Those of you who really want it and want a souvenir from Jerusalem to take to wherever, but only those who really want it, it's free after the talk. Now, I don't like to give survey lectures. I actually even hate to give a survey lecture. So I will not give a survey lecture, and instead I will just talk about the paper from this collection that I like most, and I think that it's a nice paper. So I would like to talk with you about just the paper. To get into the mood of the paper, I would like to tell you two stories, tell you about two scenarios. One of them is true and one of them is fake. Let's start with the true. So the true story is a message that I got as an email from a guy, let's call him MR, that is the way that I call him, a very intelligent guy. He has a PhD in economics, and he visited Tel Aviv, and those of you, I'm sure that many of you intend to visit bars in Tel Aviv, so that's actually just encouragement to do it. MR did it, and that's the message that he sent me after reading the paper and after he visited a bar in Tel Aviv. I went to a bar and was told it was full. I asked the bar hostess what time one should arrive in order to get in. I was told by 12 midnight. And once the bar is full, you can only get in if you are meeting a friend who is already inside. I lied that my friend was already inside without being told. I would not have known which of the possible lies to tell in order to get in. So in some sense, the paper is about MR. So what is the structure of the MR problem? The structure is the following. MR is the speaker. The hostess, the bar owner or whatever, he is the listener. And the listener wants to sort out the possible customers, and he does not, they don't want to let in everybody. Now, because of some reasons, moral, legal, whatever, they feel obliged to tell the rules that determine whether you can get into the bar or not. And she announces, she tells MR in the entrance to the bar what is the rule. The rule is quite simple, and if you have a friend inside, you can get in. If you don't have a friend inside, you cannot get in. Those of you who have been in bars, I've not, but I guess, those of you who have been in bars know that it's impossible to verify the information. It's so noisy and so, etc., etc. So the only possibility is just to look in your eyes and to hear what you say and to decide whether you are in or out. So the rule is announced. The speaker, MR, is now facing a problem, a logical, very deep problem. What to say after he knows the rules that they will determine whether he will get inside or not. And MR is intelligent enough to understand that if he is asked whether, if the condition is that he should have a friend inside, he should say that he has a friend inside. And that's what he does. He solves the problem, the logical problem, and he gets in. So you can say that this is a failure of mechanism design because everybody could solve the problem. You could say, by the way, I'm sure that every Israeli would solve the problem. Every Israeli would understand that he has to lie. I mean, nobody will even think about otherwise. In this case, MR is not an Israeli, but he's close enough to Israelis, I guess, so he solves the problem. But in some sense, of course, you can say that this is a failure mechanism to sort out between the people who are supposed to get in the bar or not. But the structure is very clear. The information is in the speaker's hand. There is a goal of the listener. The listener must announce a rule, and the speaker can either solve or does not solve the logical problem of deciding what to say in situation where there is no verification of information. Scenario B is fake. As a part of the search process for a candidate for a particular job, a principal wishes to identify those individuals whose preferences over the set of objects A, B, C is transitive. To make the story more live, I'm sure that many of you have heard about Shachar Kariv from Berkeley. Shachar Kariv, he's claiming that he has a huge experiment in the Netherlands, in which he proved, so he claims at least, that people who are more transitive are more successful in life. So this guy, this employer, took Shachar Kariv seriously and decided to check whether you are transitive or not, and according to that, you are going to be inside. You'll be accepted to the job. Now, each individual has to answer 3 questions of the type, how do you compare the object X and Y? So there is a question, how do you compare A to B, how do you compare B to C, A to C? And there are only 2 possible answers to each question. I prefer X to Y, or I prefer Y to X. So that's the question. That's the questionnaire, and the responder, the speaker, has to respond. But again, I'm thinking about a situation where the employer cannot just give you a questionnaire and test you, but because again, legal or whatever reasons, he must actually also determine the rules that announce the rules that determine whether you will be accepted to the job or not. As you will see, it's not necessarily only because of that. As we will see later, maybe that he has even an interest to do it. But let's put it aside for a second. And here are the rules, and they are very strange. We call this set of rules a codex. Whether the name is proper or not, let's put it aside. That's the name that we gave to a set of rules. And so the interpretation is the following. If you are answered that you prefer A to B, and if your answer is that you prefer B to C, then you should answer that you prefer A to C. Namely, if you answered A, I prefer A to B, B to C, and I prefer C to A, you are out. So you have to satisfy all the four rules in order to get the job.
So you must explain explicitly all the rules, or can't you just say transitive is good and then let them figure out themselves? It's like better.
It's not a matter of must or not. I'm telling you a story. So this is the story. That's the fake story, but think about it as true story. Okay? That's the story. There is no must here. Okay? So now, between you and me, of course, the speaker is not involved now in this discussion. The interpretation, of course, of R1 and R4, look at it for a second. I'm sure that all of you, if I give you 3 minutes, will be able to find what he has to say in order to get the job. Actually, it could take you, some of you probably it will take more than 2 minutes. Some of you probably will do also mistakes. We'll talk about it at the end of the talk. But in the meta discussion, let's just understand what is written here. In the meta discussion, it's not something that is told that the speaker, that the candidate is told. What is written here is that R1 and R2 means, of course, that your answer should satisfy transitivity. That's actually what the guy wants, actually, Shachar Kariv wants to discover. But there is also R3 and R4, and R3 and R4 means, in words, the meaning is B should not be in the middle. Namely, if A is on top, then B should be below C. If C is on top, then B should be below A. So in any case, B cannot be in the middle. Yeah, it can be in top or it can be in the bottom, but it cannot be in the middle. That's the interpretation of the R1 to R4. But again, the speaker is not told that. We understand it. Okay, now the story goes as follows. Here is the clever man, the candidate, and his true preferences are he prefers B to A to C. And now we ask ourselves, what a reasonable person, or what some people, or at least the person in our story, what will he do if he faces the problem and his true preferences BAC, and he wants very much the job? Let's add to it, to make it more fun, that actually is also under some time pressure. Okay, he has some sort of time pressure to respond to this puzzle. Kobe and mine approach or procedures that we assume about this candidate is the following. He prefers B to A to C. He checks whether BAC, whether to answer according to his true preferences, whether truth-telling is indeed satisfy the four rules. It does, as we explained minutes ago. So our assumption is that in this case, he will tell the truth and get the job. Okay. But now, how about this guy? He's a good guy. He's a good guy because he has he is a transitive. He has a real ordering of the alternative ABC. We want him to get the job. But the question is whether he's able to solve the riddle or not. Our assumption is that what he does is he goes through the following procedure. He goes through the rules and he checks one by one whether the truth satisfies the rules. So R1 and R2, of course, are satisfied. R3 is not, because he does prefer A to B, he does prefer A to C, but he does not prefer C to B. R4 also is satisfied, of course. So the question now, what does he do? Our assumption is that in this case, the guy tries to cheat. He wants to cheat, but he does not try all the possible 7 possibilities to cheat. He goes into it. He attempts to cheat according to the following change. Instead of saying answering according to ABC, the antecedent is satisfied. The consequent is not. He switches his answers in order to satisfy the consequence. Namely, he will answer as if the truth is A, C, B. If this is what he is going to do, then everything is fine. If he follows this procedure, he will answer according to AC, CB, AB, and he will get the job. Clear.
The requirement that he will.
The requirement is that. I said it before. The protocol is that he asks 3 questions. How do you compare A to B, B to C, and A to C? His answers as to satisfy the 4 rules. All the 4 rules. If he fails one of the rules, he's out. Okay? Clear? Okay. So this guy is a good guy, and if indeed people follow this procedure, we are happy because he gets the job. Now here is a bad guy. He's a bad guy in the sense that he has a cycle. He prefers A to B, B to C, C to A. We don't want him in. And now the question whether, in spite of that, whether he will solve the riddle. Our assumption again is that what he does, he follows the procedure that I started to describe before. Namely, he checks what is not satisfied. In this case, actually, the only rule which is not satisfied is R1. R1 is not satisfied, so he tries actually to move just to change the consequent. Namely, instead of saying that he prefers C to A, to say that he prefers A to C. Namely, his answers will be according to as if he had the preferences A, B, C. But now, when he tries to answer according to A, B, C, he fails. Our assumption is that in this moment he is desperate. Namely, that the procedure stops at this point. And he does not, of course, there are procedures, very simple procedure. The most simple procedure is to try all the 8 possibilities and to find a solution. But that's not what our assumption is. And our assumption is, and now my approach is that every model of bounded rationality, in my opinion, starts with some assumption about the procedure. The procedure is the heart of any model of bounded rationality, modeling bounded rationality. And now, whether you like it or not, of course, at the end of the talk, I will spend 10 minutes trying to give you some sort of experimental results that shows that it's not only in the head of Kobe and me, but that it has something to do with reality. But our assumption is the following. The procedures that the speakers are going to follow are essentially, there is a small but we'll put it aside in a second. Essentially, the speaker is going through the following procedure. Step 1, he examined whether the true is satisfied or not. We start with the truth. If we cheat, but if we don't need to cheat, we tend not to cheat. So first of all, it does then declare happily the true profile, and you are in at the end of the procedure. If not, then you start to look for alternatives, for other answers to respond. And the answers, but you don't try all the possibilities, but you try only the possibilities. You find the rule that is violated by the true profile, and you move, namely, it's the rule, the profile satisfied by the antecedents, but not by the consequence, and then change the consequence and check whether the modified profile satisfies the codex. If it does, you are happy. You cheat and you are happy. If not, then you try again. Maybe that there is another rule that is not satisfied and give you some hint how to change. In other words, you have a true story in life. You try not all possible stories that you can imagine, but you try only the stories that you get some hint from the codex, from the rules. You get some hints what to try. If you succeed, fine. If not, then once you iterate step 2 until you are exhaust all the possibilities. One second. And then if you exhaust the step 2, then unhappily give up or declare the truth and you're out. That's basically the procedure that we assume, Eric.
So I'm a little bit puzzled by step 2.
Yeah.
Where you say if the modified profile doesn't satisfy the Codex, iterate starting with the true
Exactly,
profile.
exactly.
Why don't you start with the modified profile and modify it some more? What's this one?
Very good. 2 answers. Number 1, actually the bold answer is the following. This is the procedure that we work with. You want another procedure? It's very fine. Another paper. That's the bold answer. Second, in about 35, 40 minutes, I'll give you some answer to it. Third, you can think about it now very K-level. One second there. Sergio, stop. I know him. So K-level is very popular these days. Level 1. But it's very important. You start always from the truth. You start from the truth. The basis is of the truth. I try to cheat, but I don't start to cheat and to cheat and to cheat and to be from Ariel to be Sergio. No, Ariel modified. Ariel modified. That's what I do in this procedure.
So, just to push back a little, you already know that the true profile is not going to work because you've already found a way of modifying, and you've already found a way of modifying it which doesn't work. So why not learn from your experience?
You learn from any experience of your life? I don't. I mean, that again, I will. I could give you many answers. Some of them could be more satisfying or not. But it's again, I'm not saying that this procedure is rational in some sense. I can say, for example, just to please you, I guess, is to say that actually think about it, the profile is very complicated. You are actually in this case, all the profiles will be possible. In life, not all profiles are possible. So if you go too far from being Eric, then it may be that you get into some story of life that everybody will understand that it's cheating. So I think that you talk with criminals, usually they don't try to go very far. They move a little bit from the truth. Okay. Yeah. Sorry? Yeah. We will come to it in a second. Okay. This was informal. Now let's go to the formal model. Let me just say before I. So actually, I'm of course inside the. We are in the mechanism design problem. As you know, usually in most of the standard approach, cheating is easy and costless and possible and etc. etc. There are some alternative approaches. I don't want to talk about them here. our approach here is that the ability to cheat effectively, people don't care about cheating, but the ability to cheat effectively depends on the way that the mechanism is constructed and framed, and I will explain it. The platform, we could actually insert this bounded rationality element into many models. We chose, for many years, we were working on persuasion models, not Bayesian persuasion, nothing to do with Bayesian persuasion, much before it. So it's persuasion models. What is persuasion models? Those of you are, after 4 hours of Eric, don't know what is persuasion situation. This is persuasion situation. He tries to persuade her. He's the speaker, she is the listener. She has the rules. He tells a story. She's not able to verify the story. He wants very much, in any case, whatever is the truth, he wants to get into the US. She, under some circumstances, she wants to let him in. Under some circumstances, she does not want to let him in. That's a basic persuasion situation. So there is a speaker. The speaker knows the profile. He knows the information which is relevant to the decision whether to let him in or not. The listener can either accept or reject the request, and he wishes to accept under certain conditions, and the letter A is the conditions under which he wants to let the guy in, and A, of course, is for acceptance. Now, this situation could be modeled in many ways. We found it in all our work, Kobe and me, we work always about persuasion situation as a leader-follower scenario. It's not the only way to deal with that. Some people deal with it as a game. No game theory here, not at all. So a leader-follower scenario, namely the listener commits to a persuasion rule. He commits. It's some set of conditions, what we will call a codex, that the profile presented must satisfy in order to accept the request. The speaker announces a profile, namely, he tells a story of life. He gives the information that the listener thinks that could be relevant, like, do you prefer A to B, do you prefer B to C, do you prefer A to C, or like, do you have a friend inside the bar? And then the listener, so it's a Stackelberg situation, namely, number 3 is automatically the listener applies the rule, and he does not have any choice at stage 3. So it's not a game. Now, if we would be inside the full rationality, then the problem is very silly, because of course the speaker is able to understand the codex and he is able to solve it. But of course, the small point, of course, is that the speaker is bounded rational. He is not necessarily able to do it, and therefore we are moving into the sphere of procedures of choice or decision making, and we are going to analyze only a very particular procedure which I've just described. Model. Now the next 10 minutes will be going to be, I would like to describe in full details the model. It's not a standard model, but don't worry, it's very simple. And bear with me about it in the next 10 minutes. I think that this is actually the crucial part of the lecture. So we talk about a codex. It's a set of rules. So we need a language for that. The language that we chose here is very, very simple. It's actually the language of propositional logic. It consists of the following. There is a set V of propositional variables, V1 to Vk. There are k variables. And think about it, if you're not familiar with the mathematical concept, think about it as k facts that are relevant to the decision. Are you economist or not? Have you been in Israel before or not? Do you have glasses or not? These are the questions that you are asked. All the variables get either 2 values, true, false, namely 1, 0. What is a profile? A profile is a truth assignment to the variables, namely it is V1 and not V2 and not V3 and V4, namely 1, 0, 0, 1, 0. The set, what is feasible, in this paper we don't put, as I said before, we don't put any constraints on the feasibility, and we assume that all the profiles are possible. Of course, in some contexts, if V1 is are you a male and V2 are you a female, then of course 1 and 0 0 are not possible. Here we assume that the k variables are completely independent and all the 2 to the power k states or profiles are feasible. Okay? Now, what is a codex? A codex is a set of propositions in propositional logic that uses only variables in V, the relevant set of facts that we ask about. And the idea is that, as I said before, the listener announces a codex, and the speaker will have to announce a profile, and if the profile satisfies the codex is in, and if not, is out. Okay? Persuasion, I mean, okay, you understand. Now, we are going to restrict the set of codexes, and I'm sure that you're going to ask me questions about it, and I think that we have answers, but be cautious about the questions, because otherwise we will be stuck too much here. I have some experience with this lecture. So, structure. Sorry?
I won't ask.
Of course, you in particular.
I remember last time when I asked.
So the answers will be the same. So the structure. A structure, the rules must be of the type something and not something, and something and not something implies something. So examples are V4 and not V1 implies V3. So it's a conjunction of variables implies something about another variable. If you are economist and you have glasses, you are invited. Okay? Sorry? No, not necessary. For example, V5 implies not V4 is also possible. There could be the number of variables in each rule is the most is k. K minus 1, the most could be in the antecedent, and only 1 in the consequent, and the one in the consequence must be different than the ones in the antecedent. So, for example, if V4 and V1 implies not V1 is not permissible. Furthermore, I think that we are going to also assume assumption. So that's assumption about what are the possible rules. There is also assumption, we call it coherence, and coherence is that it's assumption about the admissible codexes. We don't allow something of this type. We call it non-coherent. What is written here? It's written something like, if you are economist, you should have glasses. If you are economist, you should say that you don't have glasses. That's we don't allow. Of course, we do understand that this is logically equivalent to saying that you are not economist. But, so we don't allow something of this type. Also, we don't allow something of the type V1 implies V3 and V2 implies not V3. Actually, the general rule is, the formal requirement is that there are no pair of rules such that there is a feasible guy that satisfies the consequences, the antecedents of the two rules, and they lead to conflicting consequences. So if you I ask you whether you are economist, whether you are a musician, or whether you are in Jerusalem. So we don't allow something like that. If you are an economist, you should be in Jerusalem, and if you are a musician, you should not be in Jerusalem, because then Eric will raise his hand and say, what do you want for my life? I am both musician and economist, and you want me both to be in Jerusalem or not? He will complain, and we don't want the codexes to be subject to Eric type of complaints. Okay? Clear?
Are you allowed to have rules that would deduce a contradiction through longer than 2, referencing more than 2?
No, that's the only thing that we don't allow.
The only problem is if it's
That's the
and that's sort of because people are only doing the short details.
Okay, so these are the set of feasible codexes that we allow.
Why the second thing here is impossible? I mean,
What is
this
impossible?
would
Nothing is
imply that
impossible.
V1 and V2 cannot be at the same time. cannot be true. What is second line
You
there?
talk about this or about this?
This,
This?
the lower one.
Again, let me talk about Eric, okay? Because I think, look, this is a constraint that we put on ourselves on the set of feasible codexes, admissible codexes. So that's what we chose. We believe that this is not, that it's more appealing not to have this property. Namely, that if a codex has the property, if you're a musician, you should be in Jerusalem, and if you're an economist, you should not be in Jerusalem, then regarding the people who are in this room, it's something which is not reasonable in our taste. If somebody thinks differently, it's very fine with us. It's only in our taste. I think that I try to motivate it, and even Eric knows his end, so it's fine. Okay? Okay, now, so lambda is always will be the letter for the codex. So example, V1 implies V3, V2 implies V3. That's an example for a simple codex. T of lambda is the set of profiles which satisfy the codex. In other words, of course, you can think about any rule as a logical equation. So this is basically the set, of course, of solutions for the set of equations. For example, here, this is the set of the solutions for this codex, and it's denoted by T lambda. That's the set of equations. This is the answers that if you give, then you will get the job. But of course, you don't know T of lambda. You know your profile, and you know lambda. Now, let's go in. That's the key. Now, we would like to formalize now the procedure. And the formalization of the procedure goes through this definition. Informally, or partially formally, given lambda, we will, so what we have in mind is that you have S is the truth, and what you do is you are guided by lambda, by the codex, to try some other possibilities. Okay? So the possibilities, the profiles that you will try are only profiles that you are guided by the codex itself from your truth. So what you do will depend on the truth, and that's of course the key idea of this mechanism design construction. So and now informally, you are guided from S to S prime. If any change of truth value of variables in V, of a variable V, is justified by a rule. By justified by a rule, I mean that there is some rule that guides you to change this variable. Now, somebody asked me whether I can do it simultaneously or not. Yes, what we are allowing that you will change simultaneously, but not sequentially. Simultaneously, you will change more than one variable. For example, let's say that this is the codex, and let's say that the truth is 11111. What are the profiles that you are guided by the profile to try? It's of course we always we say 1111 is you are guided freely, and you are guided to 1101. Why? Because the change from 1 to 0 is justified by the rule V1 implies not V3. V2 implies not V4 justify this move. And both rules justify the two changes together, but now notice the justification is based on the antecedents are the values which are kept constant between S and S prime. So again, from S to S prime, you change some of the, you are guided from S to S prime. Sergio, you are not allowed. So from S to S prime, you change some variables, okay? You change some variables. Any change is based on existence of one of a rule that in the antecedent of the rule, there are only the variables that you don't change, And the antecedent of the rule is one of the variables that you change. That's clear? So we don't allow sequentiality that you move from one to here and then from here to something else, but we do allow that you change simultaneously more than one variable at a time if, okay? And now we come to the main definitions. We are saying that the set A, a set of profiles, is implementable if there is a codex lambda such that, in words, the good guys, namely the guys that are in the set A, are guided to a profile in T lambda, namely they are guided to one of the solutions of the set of equations. If they follow the procedure, then indeed they will give a good answer. The bad guys are not. That's the definition of implementable. Now we have also truthful implementable, and truthful implementable means that the good guys, there is a codex lambda such that the good guys can persuade, namely they are guided to, they can persuade the listener without cheating, namely if they say the truth, it's a solution. And the bad guys, even if they try not to cheat, namely they try all the possibilities, all the profiles that they are guided to by the profile, will fail. That's the truthful implementable. So that's the two concepts that we want to study, and let's move to examples. So that's my favorite example. The example here is the following. So there are three variables, and think about it. I like to have people that are either consistent right wing or consistent left wing. I don't like those people that sometimes are like that and sometimes like that. So it's 1, 1, 1, 1 or 0, 0, 0. These are the people that I would like to accept. Clear? Look at the left side, the left codex. It's very silly codex, but look at it. It's just an example. V1 implies V2, V1 implies V3, not V1 implies not V2, not V1 implies not V3. Now, what are the solutions? The solutions are exactly 1, 1, 1 and 0, 0, 0. That's clear? Everything else, of course, is not. By the way, why? I mean, if you are tired to look at it, because it means actually that your answer to the second question should be like the first, and your answer to the third question should be like the first. So if you understood that, you understand that you should answer either 1, 1, 1 or 0, 0, 0. So the solutions are the set A. Good, but who is guided to the truth, to the solution? Everybody. Everybody. Take, let's say, 1, 0, 0. So 1, 0, 0 will use this and this in order to be guided to 1, 1, 1. And 1, 1, 1 is the solution. So you understand, everybody is a solution. So in this respect, this codex is very bad. Now let's look at this codex. This codex is a little bit more sophisticated. It means what? It means that the second answer should be like the first, and the third answer should be like the second. What are the solutions? Again, the right, 1, 1, 1 and 0, 0, 0. Who is guided to a solution? Everybody except these two. Why? 1, 1, 0, of course, is guided by this to 1, 1, 1. But 1, 0, 0 is guided only to 1, 1, 0, which is not a solution. And he's not able to do the two steps that probably you feel like that he should do. Unfortunately, or fortunately, actually, not actually, fortunately, he cannot do it. Okay? So these are the two guys that are failing. Still, it's not such a great codex. Either a codex that will implement, yes, there is a codex that will implement even truthful implementation.
You don't eliminate 1, 0, 1 here.
Sorry?
So that's why you are saying it's not good enough. You did not eliminate 1, 0, 1.
I want there are only
But
two guys.
1, 0, 1 can still cheat here, guided to the truth, right?
No. No, because 1, 0, 0 will be guided only to 1, 1, 0.
1, 0, 0. 1, 0, 1, which is not written here.
Good, because it's S minus this. Everybody beside these two
Can be
is,
guided.
is guided.
But you don't want him. I thought you don't want these guys.
That's what
You
I'm
wanted
saying.
Only these two.
That's exactly what I'm saying. Therefore, it's not good enough.
Oh, okay.
Now, the question is whether there is a good enough. whether there is a good enough codex, and there is a good enough codex, not only good enough for implementation, but even for truthful implementation. And here it comes. And that's actually, now let me explain, because actually that's actually in some sense the critical move from the logic to graph theory, trivial graph theory, which actually will give us the mileage to solve or to prove some theorems. So of course there are, in this case there are 8 profiles, and we put them on the cube, and of course this is the neighbor relation. The neighbor relation, namely there is only one bit which is different between this node and this node. This is the 0, 0, 0, this is the 1, 1, 1, these are the good guys. The other 6 are the bad guys. Now how do I implement the implementation in this case? On the left side. Looks terrible, but let me explain what is going on. What we look at not V1 and V2 implies V3. What does it mean? It means that we are going, this kills the answer 0, 1, 0. Right? This rule kills the 0, 1, 0. But it does something more. It also guides 0, 1, 0 to 0, 1, 1. Now that's a key for the continuation, because such rules, we will call them complete rules. Complete rules are rules where all the k variables appear in the sentence. Okay? And every rule like that has the feature that it kills somebody, but it also guides him to something else. And now you look at the picture. The idea here is that these 6 rules are not more, not less than what's going on here. I kill this by guiding him to this, I kill this by guiding him to here, and so on. And there is here a cycle that I can create in the set of the bad guys, and that's what allows us to create the codex that will do the job. By the way, in this case, if you continue, if you do this sequentially, it will not help you, of course. You will just get into, I forgot the word in English, how to say it, but vicious circle, say it loud, vicious circle of lies. So that's what we do. Okay? So in any case, that's clear. Let me give you another example, and this is an example of something which cannot be implementable.
Each rule is only a single edge in the graph.
Pardon?
Each rule is a single edge in the graph.
Each node is a profile.
Now, each rule is a single edge in the graph.
Yes, it corresponds to I kill a single node, and I guide him to another node, another profile, which is a neighbor, of course, because I change only one.
Okay, so but only rules built with all k variables are single.
Yeah, of course, yes, and that's what I call we call complete. Complete rule is a rule. Complete rule is a rule with k variables, and again, as you said, let me repeat. So every rule of this type kills a node, kills a profile, and guides him to a neighbor. Because
Previously you showed that one can change 2 variables simultaneously.
yeah, but not here. Here you will not be able to do it.
If all rules are complete, then you cannot change 2 variables simultaneously.
Exactly. Okay? But we do allow other rules as well. And that's important for the... Okay. So let's move to here. So here actually the story is that I like decisive individual. I ask you, do you like Japanese restaurant, French restaurant, Israeli restaurant? I don't like the guys that say yes, 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 or yes, yes, no. I like the people who say yes, no, no, or no, yes, yes, namely the decisive people. Okay? So I want to only to admit them. Fine? I cannot implement it. Why I cannot implement it? By the way, the picture is here, and look at it, and that's a key to the continuation. These are the good guys, and these are the bad guys, and just a hint for the continuation, the bad guys don't have a cycle. Okay, forget of it. Now here, why this is not implementable? Well, first assume case one assumes that there is truthful implementation. Truthful implementation, namely that the good guys don't have to cheat. T of lambda equal to A. That's impossible. Why? Because 0, 0, 0 is a bad guy. It's not a solution. He's a bad guy. Namely, we have to kill him. The Codex must kill 0, 0, 0. But if he kills him, you can do it to kill 0, 0 up to permutations. You can kill him only by including either this or this in the Codex. Right? That's the only way to kill. Right? Up to permutations, of course, of the 3 to 2 and so on and so on. Sorry?
That's the case when the conclusion is V3.
Yeah. So then 0, 0, 0, in each of these cases, 0, 0, 0 is, if this is included, then 0, 0, 0 is guided by the Codex to 0, 0, 1. Now 0, 0, 1, if we are in the case of truthful implementation, then 0, 0, 1 is a solution to the lambda. So it's bad, because the bad guy will also solve the solution. The case 2. Let's say that that's not the case. If that's not the case, and still there is an implementation, that there is one of the good guys is not a solution. So let's say, again, without loss of normality, 0, 0, 1 is not in the solution. If it's not in the solution, then we must save him. It's not a solution, namely we must save him. How could we save him? We can save him only by guiding him to another good guy who is a solution. So he must be guided to either 0, 1, 0 or to 1, 0, 0 without loss of reality to 0, 1, 0. Now, if 0, 0, 1 is guided to 0, 1, 0, then it must be that the Codex include the rule not V1 implies V2. It actually also should include not V1 implies V3, but that's not important. Once the not V1 implies V2 is in the Codex, then again, our black sheep, the 0, 0, 0, again, the black sheep surrounded by the red sheep. So the black sheep here again is guided to the solution and too bad. Conclusion: this example that of a codex that of a set A which is not implementable, neither truthfully nor not truthful. Well, here, how could you? If 001 implies 010, then the only thing which is kept constant is the 0. Oh. And therefore, the only way that you can do it is by having in the antecedent the something that you keep, and therefore it must be not V1, and it guides you to change the 0 to 1. So it must be not V1 implies V2. Clear? Okay. Now, what can we do now? I mean, what we can do now is, I mean, we are within the mathematical economics cultures, and what we can do now is characterize what are the set of the A's which are implementable truthfully and implementable not truthfully, and that's what we did. Let me just say, one of the results, as you will see, is quite simple. The other one actually is not, but let me tell you about the results. Let me just, I will skip on, it will not be too technical, but again, let me again repeat on a point that I made before, which is, again, the complete rules will play an important role here. In the characterization, complete rules, namely the k variables are involved. And and again, notice that every complete rules has the feature that it kills something and it guides him to something neighbor. Furthermore, take any two neighbors, let's say this and this. Of course, there is a complete rule such that it kills this and guides it to it. That's very trivial. Clear? You have example here. 1, 1, 1, 1, 0, 0. So V1 and not V3 implies not V2, kills this and guides it to it. And that's true, of course, for every two profiles which are neighbors. Let's keep on that. Let me, before I continue to the characterization, let's be one thing which is important from my point of view, methodologically, which is I will describe now. We will get to the characterization of the sets which are implementable. You could think that actually part of the implementation will be not due, the constraints will not be due to the procedure, but due to the language of the model. So of course, let me just make clear that it's not due to the language of the model in the following sense. Give me any set X, we can construct a codex such that the solutions to the codex will be exactly the set X. Again, give me any set X, we can find some codex, forget the canonical. There is codex such that the solution to the codex will be the set X. So the language of the model by itself does not restrict the set of the sets of acceptance sets that are implementable. It's completely due to the procedure. The proof, one second. The proof of that is the following. Of course, there is an Euler circuit for the cube. So here is the Euler circuit, and now take the Euler circuit, and now you see these are the good guys, these are the bad guys. What you do is the following: you omit. You see, I omit these arrows. I omit the arrows in the circuit which are going from the good to the bad, from the good to the bad. And now, what I do, I construct a codex that will be equivalent to this graph. What does it mean, equivalent to the graph? Namely, every arrow will be transformed into a complete rule that kills this and guides it to this. Now, of course, once I omitted the arrows from the red guys, then the solutions are exactly the red guys. Of course, also, this is not a good implementation because in this case there are bad guys that are guided into solutions. But again, the point here is the methodological point is that it's not due to the language of the model. Okay, truthful implementation. Here is the basic result. Set A is truthfully implementable if and only if every connected component of R contains a cycle. Let me explain. Connected component, again, I think about the profiles as nodes, profiles of zeros and ones. Connected component, I mean regarding the neighbor relation. Neighbor, namely, two nodes are neighbors if they differ in one bit. Connected component of R, namely from every sparse connection, namely for every 2 points in the set R, you can construct a path of the neighbor relationship. A set A is truthful and implementable if and only if every connected component of R contains a cycle. Let me prove it. It's not complicated. So I do it the following way. First of all, let's see why it's necessary. Here is a bad guy. A bad guy, I need to kill him. I need to kill him, and now I can kill him by, and now there is a point that I omitted before, which I can kill him by, I kill him by having some rule that determines that is not a solution. One thing that I omitted before is that if I am guiding some bad guy to a good guy through several changes, then in particular I guide him also to every point on the road, to every neighbor which is between. So therefore, now if I kill him, I kill him by guiding him to something, but I kill him also by guiding him to a neighbor. If the neighbor is a good guy, it's not good, because then I don't implement it. So it must be that I guide. It might be that I kill him by guiding him to a bad guy. Sorry, I didn't say it correctly. Let me repeat. Why I cannot guide him to this guy? Because under truthful implementation, this must be a solution. Under other type of implementation, that might be possible, because it may be that I kill him by guiding him to this guy, but I save this guy by guiding him to another guy. But in truthful implementation, I cannot do it. This must be a solution. Therefore, that's not good, and therefore it must be that I guide him to, that I guide him to another bad guy. In particular, I guide him to a neighbor which is a bad guy, again, and now because of the coherence, that actually the meaning of the coherence in the graph here is that you cannot go back, you cannot go this way. Therefore, because of the finiteness, you get to a cycle. Conclusion: if you have truthful implementation, it must be that every point is connected by the neighbor relationship to a cycle of vicious lies. That's the one side.
I thought only complete rules, though, are ones that necessarily precisely just kill one guy.
No, but that's the point that I probably was too fast, which is if I kill something by guiding him to more than by something which through more than one changes, then there must be, I also guide him to every neighbor. Yeah, because again, we don't request that you do all the possible changes. We do request that any change that you do is justified by it. So let's say that you can do actually, you move from 11111 to 1110000, but you can also move then to 1111000. That's the point. Yes, sorry that I was too fast. Now the other side, assume that any connected component of R has a cycle, and now I'm going to construct the codex that will implement it. What we'll do is the following: there is a cycle. In the cycle, we will construct a codex such that it will kill this by a complete rule that will guide him to here, and so on. Now, the other parts of the component I will kill by going to the direction of the circle. There is one circle, so this is one way. I always go in the direction of the main square. That's one way. So, and that's the way to construct. So that's quite simple. Conclusions. For example, now in the paper there are many conclusions of this. So what we do is that this is a general proposition, and now we wanted also to have some more feelings about what is implementable or not truthfully. So again, in the paper you will find many, proposition 3 includes many parts, but here let me give you just one example. And the example here is the following: if you have, if the set of the good guys is relatively small, namely the good guys are less equal k minus 1. K is the number of variables. If the good guys are less than k minus 1, then you don't have a problem to have truthful implementation. Let me prove it. Why that? Because the set R, of course, is very large. There are only few points which are in good guys. The set R is very large, and therefore it must be connected. Why it must be connected? Because as it's basic graph theory is that on the cube, for every two guys ST, there must be k disjoint paths connecting S and T. Now, since you have only less than k minus 1 good guys, so one of the passes is not blocked by a bad guy, and therefore the set is connected. Now, the set also has a cycle. Why it has a cycle? Because if the set A includes less than k minus 1 elements, then there must be two elements in the set R, in the bad guys, which are polar. Polar, namely they different in all the components. Therefore, there must be also a path of bad guys of length k. Take the path which is the longest in the set R. construct a path of the longest bad guys in the set R. Now to get a so if the set R does not have a cycle, then that's impossible. Why? Because of the following. Look at this. The neighbor relation, of course, has the property that if this is a neighbor of this and this is neighbor of this, then there is another element which is also a neighbor of this and this. That's a trivial property of the relation. If it does not have a cycle, then these elements must be a good guy, number one. Now, we cannot continue this cycle. We cannot, this path, because this is the longest. And we cannot continue into one of the previous bad guys because there is no cycle. Therefore, all the neighbors, and there are another k-1 neighbors, are good guys. K-1 plus 1 is above k-1, and that's impossible, and therefore, conclusion. In this case, the set is both as connected and as a cycle, and therefore, that's a family of problems that you can always truthfully implement. By the way, that's related to the point of Eric before. Although what I said before that any procedure is another, give me another procedure is another paper, it's not true about one procedure because it's already appeared in our paper, which is the procedure that you continue if you move from Eric from A to B, and you move from B to C, and you so the procedure allows me to move from A to B, to be guided from A to B, and then not to go back to the truth, but also to be guided from the fake 1 Ariel to fake 2 Ariel, and so on. This procedure, we proved in the paper, that's to be implementable by such a procedure is equivalent to truthful implementation. And then, so therefore, this procedure is done. Implementation. So implementation is again, I said before, is for us it was much more complicated. I should say that in this case, actually, we almost got to the end, and then we needed an help, and Chuck Wilson from NYU was very helpful in finishing the proof here. And the proof, the general proposition is here. A set A is implementable if and only if every connected component of the bad guys, the R for rejection, I forgot to mention, includes a cycle, or it has a profile of bad guys such that the bad guy is a neighbor of another good guy, and this good guy is another good guy who is a neighbor of him. R, neighbor of S, neighbor of T. So one of the two. Either the connected component has a cycle of bad guys, or there is at least one element, one bad guy, who is a neighbor of a good guy, who is a neighbor of another good guy. Now, why it's not so trivial? Because look at, for example, let's say that this is a component of bad guys. It does not have a cycle. But there is this guy as a neighbor who is a good guy, and he is another neighbor who is a good guy. So what we will do, in principle, what we want to do is to do the following. We are going to kill it by guiding into this good guy, and we are going, this is like the gate of the component, and we are going to send all the other guys to the gate, right? But we must save this guy, right? So we must kill this guy as well, because if we keep him as a solution, then it's not implementation. So therefore, we must actually send him, guide him to another good guy.
So it's not truthful.
It's no, we talk now about truthful about implementation, which is not truthful, of course.
It's necessarily not truthful.
Of course. Well, there is no cycle, so we know that we cannot implement by truthful implementation. But now, what is the mathematical problem? The mathematical problem is that if we do this construction, it might be that there is another component here, and the gate for this component is this guy, and therefore we have also to save him by guiding him to here. And of course, and therefore the mathematical problem is in some sense to show that we can deal with the issue. At least for us, it was not trivial. In the paper, you can find 1 or 2 page proof of that. conclusion. Again, let me just a glimpse of conclusions. Here it's the opposite, namely, for example, if the set of the bad guys is very small, then there is implementation. And typically you will not have truthful implementation. Take the extreme case, there is only one bad guy. So in this case, you cannot, of course, kill him with truthful implementation, but you can do it otherwise. Okay, so that's the idea. The idea here is that you need so cheating here in this mechanism design problem is actually not a bad thing, actually, in some sense, from socially or from the designer point of view. Actually, we want people to cheat. It's a little bit in the direction of something that appears in the literature as a rationale to exaggeration. Everybody can exaggerate, so the excellent student, the very good student should exaggerate and say that he's excellent student, because only good students can say that he's very good student, etc., etc. So you understand the idea. Okay. Oh, well, I'm actually quite fast. Let me just say, so again, in the paper you can find some propositions about what more concrete what is implementable or what is not. Well, that's not so important. So let me move to the end of the lecture to a little experiment, and let me explain why did we do it. We did it because we wanted to persuade you guys that the procedure that we had in mind is not completely in our imagination, and there is some grain of truth, not more than that. There is some grain of truth. There is some traces of truth, let's say, to this procedure in experiment, not more than that. Of course, we don't claim that everybody is using this procedure. But we do, and now what are the two features? Probably I did not emphasize it enough before. It was a little bit too quick. What are the basic features of this procedure? The basic features of the procedure are: one, is that you start with the truth. The truth is the anchor. Number two is that you try profiles which you get the hint from the profile. These are the two basic components. Now, of course, we understand some people do this A to B to C and so on. Some people don't do it at all, and some people are confused, etc., etc. But we want, in some sense, that these two components, ingredients of the procedure, we want to persuade you that there are some traces to it in there. By the way, in some sense, you can see the entire exercise as a sort of exercise which is very common in economics. We want actually to sort out between the good guys and the bad guys. And in economics, we have many mechanisms and many economic ideas how to sort between the good and the bad. In this case, actually, the sorting between the good and the bad is done by the fact that the procedure starts from the truth. The fact that the procedure starts with the truth, that's actually necessary to allow us to sort between the good and the bad, because the good, actually, if they start from the truth, will succeed. The bad, if they start from the truth, will fail. If we design the procedure, the puzzle, cleverly enough in order to do the separation. Whether it's possible or not, that's the content of the two propositions. Okay, so the experiment. I'm sorry I did not, I thought yesterday to send it to you to do it yourself. Usually it works very nicely if people do it themselves. Here it is. I should say, as all my experiments, there is no money involved. No, actually, in this case, there was some money, but it's not important. Everything is done on the web, very non-kosher by the experimental community. Very right, in my opinion, the right way to do experiments, but that's for another summer school. So the crowd, actually, the subject in this experiment were students. I have a website that I constructed about 15 years ago. I will not tell you the entire story, but it contains actually students of game theory around the world participate in some sort of survey questions, and a list of students who agreed to get more experiments in order to be the subject in these experiments. Okay. Very simple, but it took us a long time to compose it. There are only two screens. Screen one, please answer the following questions about yourself. On most days, you go to bed before midnight or after midnight? It's an odd question, but I guess that most of you feel that they are identified, yeah? You are late sleeper or early sleepers, right? By the way, I have now a lot of information about when students of game theory go to bed. And actually, to be honest, actually, we changed actually the questionnaire at one point because there were too many people who went to go to sleep after midnight. So we changed it before AM and after AM to get more balanced set. Okay, so the median is around 1 o'clock. Number two, that's a very odd question. Which of the following do you prefer, cheesecake or chocolate cake? Now, I'm a cheesecake guy, clearly, no question about it. I know many people that are chocolate cake guys. I know that some of you feel that it's odd, you like both or you ate both. I still believe that most of us are identified with one of the two cakes. In any case, I force you to click on one of the two. And I'll explain in a second why we choose it. And third, actually, you were born on an odd day of the month or an even day of the month. That's something that everybody, I guess, know. Now, why did we choose these crazy questions? Because we wanted, actually, ideally, we wanted to ask you questions that you are very, personal questions that you are very identified with. The Tel Aviv University did not agree to give us access to private information about people, so we don't know the truth about yourself. So we have to elicit it. We wanted to have questions that do not include negations. So we did not want to ask people, have you been in the US or not? Because there is a sort of asymmetry between affirmation and negation. And actually there is a very interesting property of the language that there are very few unary relations that has names both for the plus and to the minus. Males and females is one example, but males and females we did not want to include it because we were afraid that, probably it's not politically correct to say it, that there are people who are from one gender who will feel very badly even to cheat that they are from another gender. So we did not want that. We want people to feel freely that they don't have a mental cost to cheat. So we did not include it, and the language does not have many examples of this type. So it's an interesting property of the language, but that's again for another lecture. Clear? That's number one. No purpose, just answer the question. Number two, terrible. Look at it. Assume now that as part of the marketing campaign you have been offered the chance to participate in the lottery. The winner of the lottery will be awarded $1 million. Ha 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 ha. Of course, it was $100 in the experiment. In order to be eligible to participate, but you can imagine the 1 million. Everybody can imagine the 1 million. You don't need the money for imagining it. In order to be eligible to participate, you must answer 3 questions about yourself, and your answers must not violate any of the following 6 restrictions. We put it this way because we were not sure that, the problem with the implication, that the mathematical implication and the regular implications are not exactly the same, and we were afraid that there will be a conflict about that. So if usually you go to bed before midnight and you prefer chocolate cakes, then you must have been born on an even day of the month. Don't continue to read it. It's awful. We did so many mistakes. Actually, in the paper at the end, we did some, actually after 50 times that we checked, seeing in the paper there is some typo because of our confusion about this. Surprise, surprise, probably because of $100, probably without it, I believe that without it, people actually put a lot of attention to this silly problem. And by the way, what do they have to do now? They assume that you very much want to participate in the lottery and you know that the company has no way of verifying whether your answer is true or true. How would you answer the following 3 questions in this case? And again, the same 3 questions. Clear? That's the experiment. Here is the Codex. You see the Codex, and clear. And now, free time. We don't restrict you. You can think about it day and night. You will not. And clear. Okay, now look at the bottom. There are 8 profiles. The 8 profiles are divided here into 3 classes. T, these are the solutions. There are 2 solutions. 8 minus 6, there are 2 solutions. Number 2, there are 2 solutions. Then these guys, these are the profiles. It's not important now the details, but believe me, there are 3 profiles that if they follow our procedure, they will solve the riddle. And these are the really bad guys, namely, these are the guys that if they solve if they use our procedure, will fail. This will succeed by telling the truth. This will succeed by cheating. Okay? Now, what is the ideal result? The ideal result is these guys will succeed by saying the truth. These guys will fail. These guys will succeed. Furthermore, they will succeed by saying the profiles that they are guiding to. Now, if I will show you such results, what would you know? One thing, that I'm cheating. That's all. Of course, people are not behaving like this, but what we want to show you now, and at least I find it extremely persuasive, that there are some traces to the procedure, and let me explain here. What you see here is the following. These are the number of, you see there are a lot of subjects here, and look at the left side. The left side, the T is the success. This is the success. The success rate of the first guys, the guys who do not have to cheat, 80%. The guys who could succeed by the procedure, 54. The guys that are supposed to fail, 36. I find it impressive. Again,
what does 80% mean?
80% of the 104 subjects who are in class T, namely, they have
to be in T. You don't know what they are.
So who declared, so you're right. They declared. I take it the declaration in the first. Again, there were 2 slides, right? In the 2 screens. In the first screen, I asked you the 3 questions.
Oh, you first asked them the question, then you gave them the codex, and then asked them again.
Of course.
Oh, I didn't get that. Sorry.
Sorry.
Okay.
Thanks for the clarification.
They were not available to go back.
So say it again, because I
they
guess
couldn't go back to the first one.
Of course
to
not.
manipulate it?
No. We thought about that. No. Okay. So again, from the 104 guys who declared in the first screen something which is in the T, and they did not have to cheat, 80% succeeded. From the guys who declared in the first screen something that if they follow our procedure they would succeed, 54% succeeded. The guys that are supposed to fail, only 36% succeeded. Okay?
how come that 20% by saying the truth would have succeeded? Decided to lie. Because they read that codex and got confused. Come on. They had to read this codex and then to figure out that it works. Come on.
What's nice about procedure, experiments, the only thing that I really learned from experiments, life is beautiful, the world is beautiful, people are different.
I would say even 80%. Even 80% is surprising that they figure out.
Elchanan said it's a good point, and I'm saying it's an excellent point. That's really the lesson from experimental economics. Now, furthermore, so 20% failed. By the way, seriously, I think it's partially. By the way, I was very serious before, but additionally, seriously, I'll give you this. I'm sure you will be confused. So there are a lot of confusions. Maybe that you tried the truth and you thought that you failed, and so on and so on. By the way, from the 80%, 71%, so it's 71, so it's most of the, so there are 9 out of 80 of the guys who succeeded, but not by saying the truth, but actually giving the other answer. Happens. And so on. By the way, the percent, no, it's 90% of the guys. So it's the top.
71 of the
Yeah, so it's most, but there are some guys. Again, everything is possible. If you have a large number, everything is possible.
Did people
But
find out personally whether they were successful in
Why it's important?
Well, as an incentive, you're not going to win the lottery, but you might care whether you got it right.
If I remember, no, we did not. No, we did not. Either they got the check or not. And usually they don't.
How many subjects were there? 500. 500. So,
Have you checked also how many people answered the way that they would look at the Codex and they would start from the first rule?
One second. We did, wait a second and then, okay. Number two, but so that's the first thing which I find unobjectively impressive. Number two, which I find more impressive, is this column. This column, I'm obsessed in the last 15 years or so to working with response time. And now it's become very popular. This was done much before it became popular. And here is, the story is the following. I'm taking the response time, the median response time of the guys who are successful in this group. Only of the successful. The guys who did not, and I calculate the median response time of these guys who are successful. And now you see, the guys who did not have to cheat, 2 minutes. The guys who had to cheat a little bit, 157 seconds median. The guys in this class, more than 5 minutes. So it's a huge difference in the procedure. Clearly, one thing that is very clear from that, that's what response time gives you. It tells you one thing, not necessarily that they follow, of course, our procedure, but there are different procedures that they use.
What does honest mean? What is the 34%?
1 second, we got only to this. Now, honest. Now, honest means that from the guys, again, from the 80% who succeeded,
That I understand. That you already
okay. Now, 29% in this group were honest. Namely, they say the truth. Namely, they say the same thing that they, in the second screen, what they say in the first screen. They failed, of course, by definition. These guys failed.
Okay.
But these guys, now, let me say, we repeated on it several times, so we have a lot of data. Let me say, more or less, about 30%, our estimation is that typically around 30% of the people, in spite of the fact that we told them to cheat if they want, nevertheless, probably they thought that the experiment is actually about cheating, and they decided not to cheat, or because they feel moral obligation not to cheat or whatever. So more or less, the rule of thumb, about 30% of the people who did not think about anything, right, everything is possible. About 30% just repeated in the second what they say in the first. Okay, now, I don't have it with me here.
Is there anything interesting about the procedure of those 317 successful? Sorry, 36%?
Yeah, yeah, that's what,
Oh, that's it.
yeah, sure.
What is the quick proof of how many people did complete the first round but didn't go to the second round? Because
Very, very few, and of course they were omitted from the, very few.
10%.
I don't remember. But,
How do these profiles look on the view? I mean, topologically, like too truthful. Is it like too truthful layer of partially truthful? And how do they look on the view?
oh, I see.
This might be just the result of random movement on the
But before, let's look here. I think that will give you, actually here you can see the answer. So, okay. So what you see here is the following. This table, there are 8 profiles, and there are okay. What does this mean? This means that there is one guy that's the truth about him is 112, and his declaration was 121. So these are the absolute numbers of the people. So what this means? This means that 33 people that declared in the first 121 also declared in the second one. Sorry about the 121. It's the two. Think about it. The 0. Okay. So they repeated on the same thing in the first, in the second. Okay. Now, so these are the honest guys, the red guys. The yellow guys, and that will give you an answer. The yellow guys, from 111, the Codex guided you only to 211. So the Codex was built in a way, of course, there were complete rules. So everything was killed and was guided to something else. these guys are not killed. These guys are killed and are guided to one of the two columns, namely to a solution. And these guys are guided into something which is not a solution. Clear? So the yellow actually tells you that the codex sends you from this to this. From this you get the answer to your question. Clear? Now what you can see here is the following. Again, so here of course you see some guys here, 1, 1, 2, 6 guys. That's the guys that I was talking before. So 9 of these guys actually. These guys solved, and now see from the 111 they went almost solely to the 211. They could go also to the 112, and by the way, both of them are neighbors. So if they just arbitrarily change one of the bits, then it could evenly likely to bring them to 211 or to 112. And here, so here, for this group and for this group, I think it's overwhelmingly there is a support for our conjecture.
The codex, or, or in the codex there was
no, but the way the order of the rules was random.
So just there was no rule that would lead them from 111 to 112.
Again, let me explain again. The yellow means that there is a rule that kills 111 and directs him to 211. There are 6 yellow because there are 6 rules.
Okay.
And there are 6, each of the rules is killed by only by one rule.
Do I see the successful R guys here? Because I would like to see what kind of procedure they use to get successful.
Of course, yes, there are, so there are, I don't know. What are the R guys?
If they do it in 2 steps or in,
It's the first 2
did
columns,
they change
no?
more than
You don't see it
you
in
allow them or something like that?
I allow them to do everything. They can do whatever.
With your procedure.
Well, it's
Those
long
are
time,
the first 2
but
columns, correct?
yes, no, but Shmulik
That's
asked,
what Shmuel asked.
Shmuel asked another question. He asked actually to give interpretation to these guys, namely, what did they do? How did they did? Did they do it by 2 steps or 3? I don't know. I don't recall. Okay, but again, my point here is the following. I think what you can see here is, I think, quite strongly, the truth is very, very. What did you want to show? You want to show that the truth is the anchor. Number 2, that there is traces, at least, to the use, or at least to the special status of the profiles, which are not only neighbors, but they are neighbors which are directed from the truth by the codex itself. That's what we wanted to show here. We have, again, in the paper, we have much more material. I will skip on that. We repeated on it several times, but I think that the conclusion in general is quite strong, at least to my taste. Okay, what next? I finished. Let me just say, some of you have seen it, so the next 1 minute, so I apologize. I repeat myself every time that I give lecture. Conclusions. These are my conclusions. That's a part of my fight against conclusion sections in economic theory. I think that I would like to encourage the young guys here, don't have conclusion sections in economic papers. In economic theory papers. Outside economic theory, I don't understand. In economic theory, to have a conclusion section is a sin, in my opinion. It's something that we are sometimes forced, and I'm not an angel. We were forced also by the editor to add some conclusion section, between publishing the paper or not, we yielded. I'm quite ashamed on these conclusions. So if you insist, there are some conclusions. The only conclusion that I really believe in is the last one, which is, as always, the model is just a fable, a story, and you can interpret it as you wish. I think the conclusion section is a big problem of the publication industry and economics. We are forced to write nonsense that usually people don't believe in. Sometimes we are overselling the papers, over application, and so on. By the way, the only advice that you can take from this paper is just how to behave in bars in Tel Aviv. That's the only thing that I am signing on. The rest is a story. Take it from it as you wish. Again, just to repeat on my speech about against conclusion sections, usually it includes two things. Number one, nonsense about some applications that people don't know anything about. And number two is, mostly, yes. And number two is some ideas for future research. Ideas for future research, I really don't understand. One of the two. If it's a bad idea, you can think about it yourself. If it's a very good idea, why should I write it in the end of the paper? Just to get some sort of ownership on the idea? Question mark, question mark, question mark. So, no conclusion sections. This is my conclusion. This is a picture which I took in Iceland a few years ago. And in some sense, I put it because I like it. That's no connection. But then after a while, actually, I noticed that it may actually fit the paper very well. Because again, the idea of the paper is to separate between the good and the bad. This is, you know what it is? I forgot the name of English, how it's called. The idea is that human beings can cross it and cows could not. So that's good guys and the bad guys here, and that's the separation. And the problem is, the cows are the bad guys here, and sorry for all the defenders of animals. And the riddle is how to cross this, whatever it's called. That's all. Thank you.